All right, so we have now already looked at the optimal contract, and we will now come to this third step, the implementation of the contract. And there are actually two different interpretations depending on the firm, whether the firm is cash rich or cash poor. And cash rich means that the R, intermediate R, is larger than rho star. This is an interesting condition for two reasons. One is that the rho star is not an exogenous variable of the model, but it's endogenous. It comes out of the rather lengthy calculation. Okay, so that means we cannot see from a firm right away whether it's cash rich or cash poor, but it depends on the optimal contract. But if lowercase r is rather large, then the firm is assumed to be, by definition, cash rich. And what does that mean? It means that the cash that the firm produces at the intermediate state is more than in optimum, in equilibrium, it should be allowed to use in order to repair the machine. So, for example, it could be that R is 1 million and the rho star is just 800,000. So that means, or let's rather cut away the zeros. Let's say R is equal to 10 and rho star 8. So that means that the firm collects 10 at the intermediate date, but it should be allowed to use only 8 to repair the machine. So how can we ensure that? And now this is one of my most liked slides, this one, for the following trick. Well, it's once you think about it, it's pretty easy. You just have to suck 2 out of the firm. What does that mean? It means that you have short-term debt of 2. So that means that if the rho is larger than 8, then, and the firm has 10, but 2 it has to repay to the outside investors. So that means it has just 8 left, and these 8 it can use to repair the machine. Okay, so it reaches exactly its rho star. So this is great interpretation or equation that the optimal level of short-term debt is just D equal to R minus rho star. And the rest, long-term debt, is then what has to be repaid in the long run. So that's just equal to R minus B over delta P. If it has a debt interpretation, if it has an equity interpretation, then well, we can also interpret it as equity. But let's stick to the debt interpretation. So that means that we have one level of long-term debt, one level of short-term debt, and there's a relation between those two. And we can make comparative statics. For example, we can check what happens if A increases. Let's do this first just verbally, and then later also try to prove this mathematically. What happens if A increases? Then so that means if an entrepreneur brings more equity to the table herself, she's richer. Okay, she has more initial wealth. How does that influence the duration of the debt structure? Will she take more long-term debt or more short-term debt? Let's see. Well, the long-term debt, the uppercase D, is independent of A. There's no A in the equation for uppercase d. But there is an a in the equation for lowercase d, but it's hidden because the rho star is an endogenous variable. So the a is hidden somewhere in the rho star. But how is it hidden? Well, let's look at the picture. Just go back. Oh, I think I clicked into the wrong direction. Here. We are in this picture. So what happens? Let me use a different color. Let's say, for example, I'm going to take purple and I'm going to take a very thin pen. So let's assume that A increases. This means that I minus A goes down. So you can see the arrow barely visible, but it's there. I'm going to make it a little bit thicker. So here's the arrow, I minus a goes down. So that means we have a line that's a little bit lower here. For example, here. This is the new a minus I. So this is the new rho star, and it's at a higher level. Rho star is going to be at a higher level. So D is equal to R minus rho star, so that will be at a lower level. Okay, so that means if inside equity increases, then the level of long-term debt will decrease, will stay the same. The level of short-term debt will decrease, and that implies that the maturity of debt gets longer. So that means the entrepreneur wants to have long-term debt. She prefers long-term debt because that means that there is less liquidation, and she dislikes liquidation. So therefore, if she has a higher A, she can afford to have a more liquid balance sheet structure, and that means have more long-term debt. Okay, how could we try to prove that formally? This is just to show you how one can do that kind of argumentations formally. So how could we do it? Well, we want to know how does D star or rho star react. So we have to check rho star is determined or given by the equation pledgeable income of rho star is equal to minus R plus, now I know this more or less by memory, integral from 0 to rho star, rho, f of rho, d rho, there's a mistake here. So there's no minus here, and there is a minus instead here. That has to be a minus. And then here's a plus f of rho star, pH times R minus B over delta P, bracket closed. Okay, and this in equilibrium has to be equal to I minus A. So I can set that equal to I minus A. And now I want to know what's happening if A increases, what's happening to the rho star? Well, if I want to know, I can do one thing, and that is I can prove this or show this either by using the implicit function theorem, which is a little bit big word. Actually, what we can do is we just say, okay, this rho star occurs here and here. That's actually a function of A, depends on A. So let's take the derivative of the whole equation with respect to A, but taking into account that rho star is a function of A. Okay? This means that, if you have an equation and you, for example, add 2 on both sides, the equation is still true. Or if you multiply by a factor of 3, the equation is still true. So that's an equivalence operation. So just keeps the equation unchanged. And the same is true for the derivative. If you have an equation, an equality, and this equality is true, and then you take a derivative of both sides of the equality, then it still has to be true because there's the same functions on both sides of the equation of the equality, so also the derivatives must be the same. So, okay, let's do this. Take the derivative with respect to a. So this gives us -1 on the one hand, on the one side, and on the other side, the r disappears. And then we have this integral that depends on rho star of a. So therefore, we have to use the chain rule. The inner derivative is rho prime of a, and the outer derivative, the same as before. That's we also have the minus sign, of course. I shouldn't forget that. So minus rho prime. I'm going to drop the argument a because, well, I'm not going to write it up because otherwise it gets a little bit messy. Rho prime of a times, and now we have the inner derivative, that's rho star times f of rho star as before, plus, and now we have the derivative of f of rho star of a. So again, we have the inner derivative, that's rho prime, times outer derivative, outer, that's lowercase f, of rho star, times ph times r minus b over delta p, bracket closed. So which variable are we interested in now? We are interested in the rho prime of a. And that's then equal to, let's see, I need a long bracket, 1 over minus rho star plus f of rho star ph times r minus b over delta p, bracket closed. Okay, I just thought I forgot one thing, and that's here the f of rho star here, f of rho star here, and there's this minus sign. So this is equal to 1 over f of rho star times 1 over the whole thing rho star minus ph times r minus b over delta p, bracket closed. All right, so we now want to know, is this positive or negative? So let's see. This here, this has to be positive. And this here, well, let's see. We know from the picture that we are here and the rho star is larger than pH times R minus B over delta P, because we're here in this interesting case, okay? Rho star is larger. So therefore, rho star is larger, so this is also positive. So that means that we have now shown that the derivative of rho star with respect to A is positive. And that means that the derivative to D, because D is equal to R minus rho, so it's exactly the opposite with respect to A, is negative. And that's the mathematical proof, okay, for derivative of D with respect to A is negative. This is something I just want to show you this once because it's a very typical tool that we do. If we have an equilibrium and we have an equation that defines the equilibrium, if we want to now know how the equilibrium changes, if we change one of the parameters, very often we can just use the implicit function theorem, and most of the time it's helpful. So let's sum up. What have we learned in this little part? We've learned that if we have a firm that is cash rich, then this firm should have a mixture of long-term debt and short-term debt. And the better the balance sheet structure, or here it is. If I have a weak balance sheet structure, that means a low A, that means I have to borrow more on the short-term basis. If I have a high A, then I can afford to borrow more on long-term. So this is a testable hypothesis. So we can check whether that's true for firms, and we can also check how this depends, for example, on the moral hazard problem. Um, that's also something that we see in here. That this, for example, uppercase D depends on the moral hazard problem. If the moral hazard problem is large, then we see that the B is large, for example, the B could be large, and then long-term debt should be lower. So that should mean that of course, we would also have to prove it because we cannot be 100% sure about that because also the lowercase d, um, the moral hazard problem B over delta P is also part of the lowercase d. So we would have to be a little bit careful here and have to prove it again. We didn't do the proof for that yet. But we can see all of these parameters, and many of them have a proxy in the data, and they have a consequence for the term structure or the structure of long-term versus short-term debt for the maturity structure of the firm's debt.